Hello, everyone, and welcome to phyloseminar.org. The current theme is on the identifiability of birth-death models, and this is the first talk in a series of 3 talks on that topic. Please use the YouTube live comment box to ask questions. I've decided to stop monitoring Twitter for questions. Today's speakers are Stilianos, Louca, and Matt Pennell. Dr. Louca is an assistant professor at the University of Oregon. He did his PhD at the University of British Columbia in applied mathematics, where he also got hooked on biology. Dr. Pennell is an assistant professor and Canada Research Chair of Biodiversity Theory and Informatics at the University of British Columbia. He got his PhD in bioinformatics and computational biology at the University of Idaho, working with Luke Harmon. Welcome both, and thank you for participating.
All right.
So let's see. So Matt, you can bring up your slides, and Stilian, you're going second, right? So I'm going to take you off.
All right. Can you see me?
Yep.
My slides. Okay. All right. I'll just go view. Thank you, everyone, for being here. It's really awesome to talk to this audience. I mean, I watch all the Philo seminars, so it's an honor to be here. Thank you, Eric, for inviting me. So today is a joint talk between myself and my collaborator, Stilianos Louca at the University of Oregon. And we're going to do a 2-part talk where I'm going to present the first part, and Stilianos will present the second part. This presentation's a kind of a summary of a group of 5 papers that we've written over the past year and a half together, in which we've really tried to dig into the fundamental limits of what we can extract about the process of diversification from molecular phylogenies. And so some of this work is published, some of this work is unpublished, and we'd like to try and walk you through it. We also know that there's going to be some rebuttal talks coming in the next month, in February and in March, and we look forward to those. And of course, given this, we understand there's some nuanced arguments that we're probably missing, and we'll look forward to seeing what these talks have to say. But for now, I'll just get right into it. As an outline, what we're going to talk about today is basically a set of these things. First, I'll give a brief introduction to the problem of diversification rate inference. Then I'll present some results on model non-identifiability and macroevolution. Then I'm going to talk about some new results that show that how this kind of model non-identifiability can explain why we so often see extinction rates equal to 0, which really makes no sense from a macroevolutionary standpoint. Then Stilian will take the talk, and he'll talk about expanding our results to include sampling through time, the case of paleobiology and epidemiology, and then kind of have some comments about why these problems we identified are such a challenging problem to work out, and also offer some potential solutions that might work. And hopefully the talks coming in February and March will fill in the gaps of some more solutions that we might have not considered. So I'm just going to jump right into it, basically, and start right here with G.G. Simpson, really pioneering paleobiologist. And he was really one of the first people to be interested in estimating speciation and extinction rates from the fossil record. Ultimately, variation in lineage diversity across time, across space, and across clades is a consequence of variation in speciation and extinction rates. And Simpson's contribution was kind of the idea of quantifying these rates through time using the fossil record. And obviously, this has launched inspired a huge research program in paleobiology, starting in the 1970s and 1980s, to fit stochastic models of birth and death to try and estimate these rates in a parametric way. And I guess where we come into the picture is thinking about how we can use reconstructed molecular phylogenies to learn about these rates. And this should probably not be news to any of you. But Sean Nee and colleagues back in the early 90s had the fundamental insight that phylogenies of extant organisms contain information about these rates, at least potentially. What we have here is a figure which shows a birth-death process. And as the clade diversifies, some lineages split, other lineages go extinct. And at the end of the day, we have a complete phylogeny. But when we look at it using our only molecular data, all we see is the reconstructed phylogeny at the bottom, which is basically the survivors. But the remarkable thing that Nia and colleagues worked out is to actually signal of these rates in the reconstructed phylogeny. So even though we don't actually observe the extinction events, we can still use parametric models to try and understand what these rates are. A classic kind of idea in this field is the idea of a lineage through time plot, which I've shown here on the right. And what we can see here is it kind of has two phases. One is a linear phase on the log y-axis here, and then there's an uptick at the end. And the reason there's this kind of change in the lineage through time plot is because organisms that are around today are the product of only speciation events and haven't had a chance to go extinct yet, whereas lineages that evolved earlier in the tree have experienced both speciation and extinction. And so by looking at this kind of graph, we can see that we can perhaps disentangle speciation from extinction by considering these two different types of distributions. And this has basically inspired a huge amount of work in this field. And not only are we looking at estimating rates from pretty simple models like the one I just showed you, where we assume birth and death rates are constant, but we can compare kind of more complicated scenarios where we might invoke ecological limits, diversity dependence, temperature-dependent rates, time-dependent rates, all sorts of variants on these themes. And this is a huge research program in macroevolution and one that I've been involved in throughout my entire scientific career. But two questions which have often plagued this field or been really hard to resolve is to say, which of these possible candidate models can we potentially tell apart with phylogenetic data? And the second question, which is related, is how robust are parameter estimates if we misspecify even a little the actual generating process? We know, for instance, that rates have not been constant throughout time. The geological record is clear on this. Rates have changed quite dramatically over time, and so the idea that we can fit a constant rate model is obviously a simplification. But we want to know basically how wrong would we be if we did misspecify the process. And so answering these questions, there's been a ton of papers on this topic. And these kind of have taken the guise of two types of approaches. The first is simulation studies. And there's a lot of these, and they're really great, saying, okay, we simulate under this scenario where you violate the assumptions just a little bit. How far off are we? And trying to gauge how we're doing. The second kind of approach is to take case studies, especially cases where we have a pretty well-sampled fossil record, let's say Cetacea, and say, compare what we think from the fossil record to what we get from molecular phylogenies. And there's been a number of case studies on this point. But both of these approaches are, while useful, are really limited in terms it's really hard to make general statements about the general reliability of these methods. What scenarios can we tell apart? When can we tell them apart? And how good our parameter estimation is. And so what Stilianos and I wanted to do was create like a general approach in which you can answer these questions in a more holistic way rather than looking at single case studies. Can we say something about the general properties of these models? And this is where we're going to start here. So we're going to start with a very simple model where speciation and extinction rates vary through time. In this simple example, we can come up with any arbitrarily complex example we want, but speciation here is a linear function of time, and extinction rates are constant throughout time. And we can specify any kind of arbitrary time dependency we want. We're going to here only consider the models where there's lineages. It's a homogeneous birth-death process. That is, all lineages have an equal rate of speciation and extinction, although these rates vary through time. And we can perhaps talk later about how this extends to multi-type models. So previous researchers have developed some general equations for writing the likelihood of such models in terms of the branching times of the phylogeny. There's a nice paper by Elaine Morlan in 2011, and there's other papers which have basically, for any time-dependent model we can come up with, there's a pretty easy way to write the likelihood in terms of the branching times of the phylogeny. And this is all well and good, and this has inspired researchers to develop a lot of complex and interesting models for describing how speciation and extinction rates vary through time. But I guess the genesis of this work was kind of an accidental discovery, or a discovery that we tried to do for some other purpose, was that we can actually write down an alternate way, the likelihood in an alternate way. And it turns out that the likelihood of a phylogeny can be written purely in terms of the deterministic lineage through time plot. That is, the lineage through time plot we expect without stochastic variation. And this actually likelihood is identical and equivalent to the likelihood using branching times. And I'll just say that this encapsulates all the information in the tree about rates. It turns out there's no information beyond the LTT with regard to rates for a homogeneous birth-death process. And so if you can write the likelihood in terms of just the deterministic lineage through time plot, you can also write the only information in the tree is also the observed branching times, or the observed lineage through time plot. We'd also kind of like to do a shout out here to Lambert and Stadler, who have this paper in theoretical population biology, which also derived a similar likelihood, but we weren't aware of at the time. But they derived a similar kind of approach for calculating likelihoods. But a consequence of thinking about things in this way is that any two models with the same deterministic lineage through time plot will actually have the identical likelihood. And this will be true of any data set of any size. So it's not a property of the data set itself, it's a property of the two models. So recognizing the fact that any two models with the same deterministic lineage through time plot will have the same likelihood means that any two scenarios which produce the same plot will be completely indistinguishable by any statistical measure, because this captures all the information in the tree.
Can you help me understand? So I just want to understand the deterministic adjective. Is it, I mean, it's not an expectation. Is it sort of like a large sample limit? Like if we were to run this? Like, yeah,
so I would say, how would I say this? It's basically like a trick for deriving the likelihood. We're not making any approximations or anything like that when we derive the likelihood. But it would be, yeah, sure, I guess the expectation or the large sample limit.
Okay.
For what the curvature should look like.
Great, thank you.
But again, this is not an approximation to the likelihood. It's identical to the likelihood formulated using different techniques. And we'll call any two models with the same deterministic lineage through time plot will have the same likelihood. And so we'll call these two models congruent. There's no information in the tree which could possibly distinguish between these two scenarios. So the challenge is to figure out how to find other congruent models. And it turns out there's actually a really nice relationship here, is that congruent model sets all share the same mathematical properties. And that's that any two scenarios where speciation rates and extinction rates vary through time according to some function will have the same likelihood if and only if these two things are the same. One is they share the same curvature of this meta function here, or composite function, which is lambda minus mu plus the derivative of lambda, and the same starting condition of lambda speciation rates at the present multiplied by the sampling rate. So any two scenarios which have the same function for the first type and the same value for the second equation will, by definition, have the same likelihood. And so what we've basically found is that many different scenarios will satisfy this equation. And we can kind of play this game a bit and do this infinitely. In fact, is what we have here in panel A is in black, we have the deterministic lineage through time plot. And in the different colors, the different blues and reds, we have 4 different scenarios that show how the number of species has accumulated through time. And what we can see is if we look at the speciation rates in the panel B, the extinction rates in panel C, or the net diversification, lambda minus mu, in panel D, all of these 4 scenarios have very different rates and very different dynamics, but they're by definition indistinguishable from one another. These all produce the exact same deterministic lineage through time plot, and therefore have the exact same likelihood for any data set we can come up with. And this doesn't depend on, so even if we have infinitely large data, millions and millions of taxa, will never distinguish between these scenarios. And what's really shocking is how different these can be. Here's an example. These models fitted to a seed plant phylogeny containing some 78,000 taxa. And what we can show is that this pattern, a model in which speciation and extinction rates increase through time, shown in these blue dots, has an identical likelihood to a model where speciation and extinction rates decrease through time. And so even though this tree has some 80,000 taxa, we actually can't distinguish between these two seemingly very different scenarios. And this is really was shocking to us how different these could be. And it's really caused us to try and rethink what we're doing and what inferences we can actually make from molecular phylogenies. And as I said, no matter what the tree is, you can never distinguish these scenarios from phylogenetic data. And so we had this conceptual diagram in our original paper here, which kind of highlights some weird property of thinking about, instead of just single models, thinking of congruent sets of models. Is that what will happen oftentimes is estimators, whether they be maximum likelihood or Bayesian estimators, will converge to a model closest to the model in the congruent set that's closest to that model, or the estimator, I should say, but not necessarily the generating process itself. So we imagine here the generating process is this red dot. We can consider two cases, one in which none of the models in our congruent set, in our model in the set of compared models, is in the congruence class of the generating model. And if we compare the model fits these different models, we'll find a model which is closest to the congruence class is our best supported model, but not necessarily the model that's closest to the generating process itself. In the even more extreme case, if we actually have a model in our data set, which it actually happens to be in the same congruence class as the generating process, there's going to be strong support for that model in the green circle here, even though that may be very different dynamically than the model that's closest to the truth. So this suggests that estimation methods can be really getting the dynamics really far off. And in our original paper, we presented this as a theoretical possibility, but we've subsequently shown that we can actually show this happening in real data. And where we kind of got the idea for this is that there's this really weird pattern in phylogenetic analysis of diversification that we often see diversification rates or diversification studies estimate extinction rates to be 0. We know this is inconsistent with the fossil record. This has been remarked upon many, many times. But we still see this all the time in data sets, including data sets that are pretty big. And so it really is strange why this happens. And while there's been a number of studies which have done simulations of diversification rate estimates, nobody has quite nailed down why this is the case. I'm not going to go into the details, but here's a really nice study by Jeremy Beaulieu and Brian O'Meara in which they simulated data sets under a variety of different models. And what you can see here is they oftentimes get inflated, or they often find 0 extinction rate estimates, even though the simulated model is quite different than that. And they were really kind of, then they were honest about it. They didn't have a full explanation as to why this happens. And it's definitely not clear why this happens in real data. So we wanted to try and figure out, can we explain this pattern using our kind of model identifiability results? And the key here is to look at this figure here, this kind of cartoon, and to recognize that just mathematically speaking, this congruence class also contains models with negative extinction rates. These are biologically implausible and meaningless, but nonetheless, they mathematically satisfy the equation that generates the same deterministic linear tree time plot. And so it could be the case that the most likely estimate for extinction rates can be negative. And this is something that has been pointed out also by Tanya Sadler and Mike Steele in a slightly different context. But here what we have is a phylogeny of 294 hummingbird species, I believe. And what we find here is if we just fit constant rate birth death models, the maximum likelihood estimate for mu, turns out to be negative. And we've looked at likelihoods across all the different parameter space, and the maximum likelihood estimate is a negative mu, I should say. And this is not a case of simply an inadequate model, because if we do some parametric bootstrapping, we find that the distribution of trees and distribution of edge length, etc., predicted by the model, including negative extinction, perfectly matches the tree. So this is a really adequate model by basically any measure. So what we did to try and investigate whether this could be driving patterns of zero extinction rates is to consider this. So in panel A, what we have is we've simulated data in which speciation and extinction rates vary through time according to a pretty simple process, here at Ornstein-Uhlenbeck process. And then what we fit was a standard suite of kind of models with specific functional forms, which didn't exactly match the simulating model, but were pretty close enough and pretty flexible enough that they could at least approximate it. And we could show that they could approximate it using some parametric bootstrapping again. So this is not a case of model inadequacy at all. But what we found here is if we look at panel A, we have the true simulated speciation rate at the present and the estimated speciation rate at the present. And what we can see is very little correlation between the two. But we also find this kind of clumping of estimates at the zero extinction mark, just like we see in real and simulated data. And this is the best fit model of our candidate set, I should say. But then what we can do in panel B is actually allow our maximum likelihood estimator to search in the space of negative extinctions. And what we can find here is basically the figure in A is basically it releases the valve and a bunch of these estimates fall into the negative realm. So it appears to be that they are favoring maximum likelihood estimates of zero extinction, but it's just hitting the boundary at zero. Okay, that's strange. And what we can show in panel C is, yes, it is indeed hitting the boundary here. That's why we're getting these results of zero extinction, is because they should be negative, but they're just hitting the boundary of zero. But how is this related exactly to this congruence class idea? Well, when we fix the speciation rate to be the true speciation rate, and just transform estimate the mu in that case, we always get the estimated mu, even if we allow for negative extinction rates, to be almost perfectly what the true generating process was. So this suggests that if we're estimating these parameters freely, we're getting into negative extinction, but those models are congruent to models that correctly approximate the generating model. And here's an example of this, and I'll give it to Stilianos in 1 second here. Is that if you take the left-hand case here, the generating model here is the lambda in the black lines and the mu, the extinction rate, in the red lines, solid lines. And here the best fit model was a linear model where lambda changed linearly and mu is constant. As you can see, when we constrained mu to be greater than zero, greater than or equal to zero, we got a zero estimate of extinction rates. And we got a linear decline in speciation rates, but these are very discordant with the actual true generating values, even though the parametric bootstrapping suggested that this model is perfectly adequate to explain this data, as you can see by the match between the tree linear distributed time plot and the implied deterministic linear distributed time plot of our parameters we fit. Likewise, in panel B, we show that if negative extinction rates are allowed, the estimate does, again, for extinction, fall to a negative value. Speciation rate has now a positive trajectory, but still very discordant from the actual true generating model. But what we can do here is if we fix find the congruent model of our set in which we fixed lambda to be the correct value and just transformed the mu accordingly, it actually approximates the true generating value quite well. So we haven't, what we've shown basically is that the reason we see these negative extinctions or the zero extinctions when we put a boundary is simply because it's finding a model which is in the same congruence class as the generating model.
Matt, can you just, I mean, I can imagine like writing down a likelihood and plugging in a negative extinction rate, but I mean, does it actually make sense to realize a tree from a model with a negative extinction rate? Is there such a process that you could do that would?
Yep, it works.
So,
so it totally works. It's pretty wild.
Wait, but what does that actually mean? So I'm growing my tree and it has a negative extinction rate. How do I actually sample from that?
How would I explain this? Maybe I'll let when Stilian transfer, I'll let him. Okay. I'll let him take on this question because I think he'd be better answer it than I would.
Right, cool.
But like, yeah, it makes no sense but you can actually do it.
Okay.
And then Stilian will jump in and explain it in a better way than I will. I know.
All right.
So this is pretty wild, actually, and it's pretty strange. And so it suggests that this negative extinction rates are in the same congruence class as these positive extinction models, which actually match the data quite well. And this we took 151 trees. Here on the left is all trees, and B is the ones that were completely adequate by parametric bootstrapping. And as we can see, even though we don't know the true generating model in the tree, we still see the same relationship between models estimated where extinction rates allowed to be or constrained to be positive and those where it's allowed to be negative in both all the trees and in the ones which are totally consistent with the applied model. And with that, I'm just actually going to give it to Stilian and let him take over from here.
Great. All right. Stilian, so I've got your screen shared. I think we're good to go.
I always wanted to say this. Hello, world. All right. Hello, everyone. Before I continue with the original plan, I just want to clarify something on the question that was just posed. We're not actually generating trees from models with negative extinction rates. We're generating trees from the constrained model with zero extinction rate. So when we say in our paper, and what Matt meant in his talk, is that the wrong constrained model with zero extinction rate cannot be rejected based on the data using various parametric bootstraps. From the model with negative extinction rates, obviously we cannot generate trees. We can only calculate the likelihood.
Okay, so it's congruence on the level of the likelihood calculation, which is sort of formal. It formally makes sense if you just take the original equation and plug it in a good value.
Yeah.
Okay, and also I just want to remind people, feel free to post questions on the YouTube chat box. All right, take it away, Stilian.
All right, thanks, Matt. Thanks, Eric, for the great invitation and for this opportunity. I'm gonna switch gears to a different but related theme. I'm going to talk about the case where trees are sampled serially through time. This is obviously a generalization of our previous work. A lot of people in the community have also asked what happens with the situation where we are able to sample tips from the past. And in fact, we also kind of hypothesized in our one of the first papers we wrote about this, that perhaps fossils could serve that role and resolve the congruency issues that we discovered. So here we go. We actually figured it out. So trees where tips are sampled serially through time are commonly available for rapidly evolving pathogens such as HIV or SARS-CoV-2. They're sampled from patients over time in that case, and they're increasingly being used to estimate epidemiological parameters such as the effective reproduction ratio. So that's why they are so important, actually. Now, on the one hand, the inclusion of lineages from previous times could provide the necessary information to resolve the identifiability issues that we face with extant trees. On the other hand, however, the efficiency or the rate at which we sample lineages through time might be unknown itself. So it might need to be estimated from the data. Now, this added uncertainty could, in principle, cancel out the additional information gained from the serial sampling. So to investigate this important issue, we considered one of the most fundamental and commonly used cladogenic models for epidemiology, the birth death sampling model. That's how we're going to call it from now on. In this model, there are basically 3 free parameters, each of which could, in principle, vary over time. And in many cases, they do vary over time. The speciation rate lambda, that's the rate of transmission events per host per time in the epidemiological case. The extinction rate mu, the rate of host death or recovery per host per time. And the sampling rate psi is the rate of tips sampled per host per time. We're assuming that sampled lineages are immediately removed from the pool. This assumption is common in epidemiology. But if you want more details on the concrete definition of the model and its assumptions, we encourage you to check out Eileen McPherson's preprint indicated at the bottom of this slide. Now, the likelihood of a bifurcating tree under such a model was recently derived by Eileen, and you can find the derivation in the preprint indicated below. And it's interesting to note that this likelihood depends solely on the tree's node ages and tip ages, but not on the tree's topology. Now, this is analogous to the macroevolutionary case, where all tips are sampled at the present and where the likelihood of an extant time tree only depends on the node ages. Okay. Now, using mathematical techniques similar to the macroevolutionary case, by which I mean the case where the tips are sampled all at the present day, we discovered that the likelihood function of any birth death sampling model can be written entirely in terms of only 2 composite model parameters, which we called the pooled speciation rate, which is more or less the relative rate at which we expect to see nodes in the tree, and the pooled sampling rate, which is more or less the relative rate at which we expect to see tips in the tree. For details, you should consult the preprint listed at the bottom for detailed definitions of these 2 pooled parameters. But you can already see the analogy to the macroevolutionary case that I'm going to get at. These 2 pooled parameters are entirely properties of the model. They have nothing to do with the data, and they can be readily calculated using the original parameters lambda, mu, and psi. Okay. And if you know these 2 pooled parameters for a model, you can calculate its likelihood function for any given tree.
So intuitively, the pulling is the idea is we have the speciation rate and it gets pulled by the extinction rate over, or the sampling rate, or what is the intuition between the words?
So if you write out the formulas for these 2, they look very analogous to the pooled speciation rate that we've introduced for the macroevolutionary case. Okay. Other than that, we just use the word pooled to point out that analogy.
Okay.
But I would say the interpretation in terms of pooling is a little bit more complicated than for the macroevolutionary case. We could have called them something different. But they're basically the speciation rate, the actual speciation rate lambda, multiplied by the probability that a lineage would appear in the tree, which is the same as in the macroevolutionary case. And for the pooled sampling rate, it's the original sampling rate divided by that probability. So here I'm just showing the likelihood function written in terms of these 2 pooled parameters, just to show you that indeed we can write them. We can write the likelihood in that form. So, in analogy to the macroevolutionary case, we henceforth will call any 2 birth death sampling scenarios congruent if and only if they have identical pooled speciation rate and pooled sampling rate. So any 2 congruent scenarios will generate trees with identical probability distributions and cannot be distinguished using time trees alone, no matter how large. This is exactly analogous to the macroevolutionary case. Now, it is easy to construct a myriad of alternative, markedly different, and yet plausible congruent scenarios. I'm not giving you the formula for doing so. You can find that in the preprint, but it's easy. You can, for example, choose some arbitrary extinction rate and then just calculate the corresponding lambda and psi, and you get a congruent model. For example, in this figure shown here, you can see various alternative congruent models. So each color corresponds to a different congruent model, and they're congruent to the black curves. In the first row, we're seeing congruent models to the black curve, and in the second row, we're seeing another set of congruent models to again another scenario depicted by the black curve. I should emphasize that the pooled speciation rate and pooled sampling rate themselves are asymptotically identifiable. That is, one can estimate them sufficiently accurately if only we have sufficiently large trees. But they do not contain enough information to reconstruct the actual epidemiological history in terms of lambda, mu, or psi. So the bottom line here is that if each of lambda, mu, and psi, so the speciation rate, extinction rate, and sampling rate, can vary over time, then in the absence of further information, we cannot jointly estimate all three based on serially sampled time trees alone.
And if
this is similar.
Do you know if we do have sort of knowledge of what the sampling rate is, then we can get the other two?
Absolutely, and I'm going to talk about that later.
Okay, sorry.
Yeah. Now, this is similar to the macroevolutionary case. We cannot jointly estimate the speciation extinction rate profiles from extant time trees alone. So here now we have three parameters instead of just two. We cannot jointly estimate all three from extant from series sample time trees alone if we know nothing about either of them. It is worth mentioning that congruence classes can also be parameterized, in other words, uniquely defined using an alternative pair of composite parameters. The deterministic branching density, which is roughly proportional to the probability distribution of nodes over time in the limit of infinitely large trees. And the deterministic sampling density, which is proportional to the probability distribution of tips over time. So these are sort of analogous to the deterministic lineages through time curve, if you want. They contain similar types of information. Any two birthday sampling scenarios are congruent if and only if they have identical deterministic branching density and deterministic sampling density. These two parameters are, again, asymptotically identifiable, but they do not contain enough information to reconstruct lambda, mu, or psi. The only benefit to the pooled speciation rate, pooled sampling rate, is that they are somewhat easier to interpret, and it turns out that they're numerically more robust than the pooled speciation and sampling rate. It's just easier to calculate those two numerically. But mathematically, they contain the exact same information. Now, to demonstrate the implications of all of this, we actually went out and simulated a simple epidemiological scenario shown here in these blue curves. And then we used BEAST to fit a birthday skyline model. That's a type of model where lambda, mu, and psi are described by piecewise constant curves through time. I mentioned that during the fitting, we fixed the present-day sampling fraction. That's a derived parameter of the model commonly considered in epidemiology, to its true value, to account for all identifiability issues known previously for skyline models. Now, these plots here show the true epidemiological scenario, so the true lambda, mu, and psi, that's the blue curves. And the posterior credible intervals generated by BEAST based on the simulated sequences. It was about 590 sequences in total. So quite an impressive data set. And as you can see, BEAST failed to even approximately reconstruct the true epidemiological history. Now you might think, the true scenario, the blue curves, is clearly not of a skyline type. So this is simply the result of model violations. No wonder Beast couldn't estimate that properly. But that conclusion would be wrong for two reasons. First, in general, our mathematical models never ever perfectly describe reality, certainly not macroevolution or epidemics. The only thing we can ever hope for is to approximately represent reality. So if we fit a skyline model to data generated by this hypothetical epidemic that we considered, one would at least hope to approximately reconstruct it, more or less as shown in this figure on the left for the speciation rate, especially for such a large data set of almost 600 tips. Instead, what we got was this, a complete mismatch. Second, we performed multiple posterior predictive simulation tests, and none of the tests was able to reject the fitted models based on the data. In other words, the data were adequately described by the fitted models, despite the models being clearly wrong. So what happened really? Now, this is the point where Houdini would pull the rabbit out of the hat. So I'm going to pull a rabbit out of the hat. When we calculated congruence invariant parameters of the posterior models, such as the deterministic branching and sampling densities, we found that Beast actually estimated these very accurately. So what you can see here is the deterministic branching density. Blue is the true profile, and the shades depict the median 50% and 95% credible intervals by Beast. And the same here for the deterministic sampling density. And you can see quite a good agreement between Beast's predictions and the true profiles. So Beast did indeed converge to the true congruence class of the true scenario, just not the true scenario itself, which is exactly what Matt was showing you in that conceptual figure. So Beast did nothing wrong. It actually found the congruence class, but there was no way it could do better. Now, this is fully consistent with our general prediction that any statistical estimation tool based solely on time trees will at best converge to the correct congruence class, but rarely to the true epidemiological scenario. Now, you might still think, well, there just wasn't enough data somehow. Now, this conclusion would also be wrong for two reasons. First, if it was just a matter of insufficient data size, then the posterior credible intervals should have been much wider, at least wide enough to largely cover the true profiles and properly reflect the remaining uncertainty. But they weren't. Now, here the credible intervals suggest that we quite accurately inferred the epidemiological history. There's no indication of the actual error that we're facing. Second point why data size wasn't the problem is that these problems persist even when we fit birth sampling models to much larger trees. So in this example shown here, we fitted a birth sampling model with piecewise linear profiles to a massive time tree with over 50,000 tips using maximum likelihood, and while selecting the optimal number of inflection points according to AIC. I just want to mention that these massive analyses can be done efficiently using the R package Castor. Now, as before, the fitted profiles for lambda, mu, and psi, so that's the dashed lines here, differ strongly from the true profiles, the blue curves here. In some cases, even by orders of magnitude and with wrong trends. While, on the other hand, the congruence invariant deterministic branching and sampling densities shown here below are very accurately estimated. So as before, we correctly inferred with the maximum likelihood fitting the congruence class of the epidemic, but completely failed to infer the actual epidemiological dynamics. Now, you might wonder, what if we applied some sort of regularization? some type of penalization of complexity. Could this help determine the proper scenario somehow? I mean, it works in many other situations. The answer is no, clear no, for at least two reasons. The first reason is that penalization of complexity is used to avoid overfitting. In other words, avoid adding spurious complexity when the data is limited. But this is clearly not a problem of overfitting. Indeed, even very simple models fitted to huge data sets generated by simple scenarios can easily yield wrong trends and be off by orders of magnitude. See, for example, our previous slide. Very simple scenario, simple model, tons of data, and completely wrong answer. The second reason is that as the data size increases, penalties for complexities generally become less important. And the promise of penalization of complexity methods or regularization methods is that eventually the true or the best model will be favored, regardless of complexity. Now, this promise is clearly not met here. Even for infinitely large data sets, there will be no guarantee that we will even approximately infer the correct scenario. So, why did these issues remain largely unnoticed until now? Well, the first likely reason is that parameters of congruent models are related not through some simple algebraic equations, but through differential equations. So it's not trivial to see. So the slope of one parameter correlates with the value of other parameters. It's a bit more complicated than just an algebraic correlation. This applies both to the macroevolutionary case as well as the epidemiological case. The second likely reason is that many simulation studies fit the same functional forms as the ones used to generate the data. So simulation studies that want to check how well an estimation method works, for example. In that case, for sufficiently large data sets, the fitted profiles closest to the true congruence class will also tend to be close to the true profiles. So fitting would appear to work fine. But in reality, the true scenario rarely exactly follows our simplified functional forms. So the fitted profile close to the congruence class can be very far from the true scenario. For example, if one were to simulate data using a skyline model, here in the figure on the left, that's the blue curves, and then fit a skyline model to those data, then one would typically accurately reconstruct the original profiles. That is, provided sufficient data. But if the data were generated by even a slightly different model, here on the right, qualitatively the same, but just slightly different functional forms, one can easily get a drastically different estimate, even if in principle a skyline model, the one that we're fitting, could have approximated the true profile well. So while skyline models could probably approximate most realistic scenarios out there, fitting such models can easily yield very wrong estimates far from the true scenario. Now, this is not a criticism of skyline models. The same would apply to any other type of functional forms fitted, such as piecewise linear profiles, which arguably are also quite generic and able to capture most typical epidemic variation over time. And if you fit any other type of model, you can easily get a whole different answer. So even qualitative inferences, for example, about trends or the order of magnitude of the speciation rate, become very sensitive to the choice of functional forms that we fit, and in any case, completely unreliable. The good news is that if we can constrain the sampling rate or the speciation rate to its true value over the entire time period, so the actual profile, then all other parameters become asymptotically identifiable. In other words, the congruence class collapses to a single model, and we can, in principle, recover that with sufficient amount of data. Now, such constraints could come from clinical data or from seroprevalence surveys. In this example here, we fixed the sampling rate psi to its true profile over time. That's here. And then use maximum likelihood fitting to estimate the other two parameters. And we did obtain quite accurate estimates of those other two parameters here for lambda and mu, because now we collapsed the congruence class. Now I want to bring forward 2 points of caution here. There's little use in fixing a parameter to a wrong value just for the sake of fixing it, since then the other parameters will be wrongly estimated. So it's not just about fixing a parameter, it's about actually fixing it to its true value, at least roughly. And second, while priors can be used to specify constraints in a Bayesian context, these priors must be much stricter than commonly used wide priors. So they need to use case-specific information, since any uncertainty in the prior leads to a similar uncertainty in the predictions, regardless of data size. So how do we move forward? Well, we need to find new data types separate from trees to constrain our models. We need to look for similar potential issues in other evolutionary and population genetic models. And we need to remember that adding free parameters to a model allows for more realism, but this does not mean that all of these parameters will be jointly identifiable from the available data. If you want to find out more about all of this, we encourage you to check out our various papers on the topic. If you're skeptical, we encourage you to visit our challenge website. I promise it'll be fun. And with that, I want to thank our collaborators, funders, and our audience.
Thank you very much, both of you, for a very interesting talk. So we will continue to take questions. There's one question on sort of the first part of the talk, but I'll just ask one quick question about the second part, which is, did you try temporal smoothing for the beast exercise?
No, we fitted a birthday skyline model. So then we took it at face value that this is the value at every one of those time intervals. In the particular example shown here, we had 4 time intervals. For the jumps between the between two adjacent segments, we assumed that the jump occurred over a short period. So we linearized in between. So it wasn't an instantaneous jump. But other than that, no further smoothing. But so you're referring to smoothing after the fact. So after from the posterior models, then smooth those.
No, I mean, let's see. I mean, I'm not a pro about this, but there's like the generalized skyline plot where they look at sort of, they allow there to be some sort of correlation between pairs of what the skyline values are. So
to penalize jumps.
Right. If I understand,
well, that's a type of regularization, if you want.
Right.
In some sense. No, we didn't try that, but as I explained, we don't expect that to have changed anything. I mean, yeah, you saw that Beast did correctly infer the congruence class, and that's as good as it could have possibly gone.
Right. I understand that part, but I mean, I still think that it would be interesting to try out and to sort of strengthen your results if you still get sort of bad results with temporal smoothing, because it is another sort of type of prior in my mind, that you're sort of assuming that the interval between the jumps is not so big.
Hmm.
Anyway,
yeah.
Let's see. So I'm just going to start. So Steve Haddock asked early on, in the first part of the talk, is there any relationship between negative extinction rates and underestimated speciation rates? And maybe I'll just pop Matt on here too. And it didn't appear so in the graphs. Does that question make sense? I'll just, oops. Is there any relationship between negative, is there any sort of compensation in the speciation rates for the negative extinction rates? Does that make sense? Hello?
So I can answer that if we want to.
Matt, I've turned you on too, Matt, if you want to answer that question.
Sorry, I can't hear Eric right now, so you have to take the questions.
Oh, okay. Maybe Stilian, you can?
Yeah, so yes, there would be a negative relationship, especially for the simpler cases where if you fit, for example, constant rate birth death models. Matt showed one figure for the hummingbirds tree, and we showed you the actual likelihood surface for constant rate birth death models. So there's only two free parameters, the constant mu and the constant lambda, and you could see there is somewhat of a negative relationship, but remember there is a clear global maximum in the likelihood. It's not like there's a ridge visible in that likelihood. So there is a clear global maximum for a negative speciation, for a negative extinction rate and a positive speciation rate in that case. It's very unlikely in general that your congruence class intersects with your model space to actually see a ridge in your finite dimensional parameter space. We explained that in one of the supplements in our macroevolutionary paper. If you just come up with a finite set of with a set of functional forms for mu and lambda, parameterized with a finite number of parameters, let's say exponential growth or linear or skyline or whatever, it's very unlikely that there will be combinations of parameters leading to congruent models. That's one reason why it's been missed.
All right, thanks. Peter Ralph asks, how about assuming that sampling intensity is constant? And B, inferring the birth and death rates, and then C, putting a prior on sampling intensity through time and adding this uncertainty to B. I'm trying to digest that. Not sure if I really understand that.
So my quick take would be that if you have reasons to believe that the sampling intensity is roughly constant, so in the epidemiological case that psi is roughly constant, there might be some epidemics, for example, where we can assume that we're actually detecting most cases. Perhaps HIV is one of them. We can probably assume nowadays that most cases we sooner or later detect. Sorry, actually, in this case, I'm not referring to the sampling intensity. I'm referring to the sampling proportion, which is a part of a different set of parameterizations for both the sampling models. So in that case, sampling proportion, you could assume that's close to 1. You put that as a constraint or as a very strict prior in your Bayesian analysis, and then yes, indeed, you recover the correct values for the remaining parameters. For the sampling intensity, I'm not sure if the assumption that it's constant is warranted in most realistic cases, because usually we increase our effort to detect the disease as we move through the epidemic. COVID certainly has shown that testing effort has increased over time. So I don't think we can assume that the sampling intensity has been constant.
Yeah. I think he's thinking of, he also says, I should be looking at this comment too, would it tend to produce interpretable credible intervals or would it be unreasonably big? I'm still not sure if I quite follow, Peter, sorry. It's somehow I feel like you're implying that one could sort of start with a constant sampling intensity assumption and then correct it after the fact somehow. using a prior on the sampling intensity, but I don't totally get it. Maybe, I don't know, maybe Peter, you can make more explanation. And while he's doing that, I will just wonder if you could suggest a little bit more about what are the sort of non-tree data types that you can imagine being helpful for being able to resolve things. I mean, obviously the sampling intensity is a big one. But is there something, when you said maybe we should also be collecting other types of data, did you have anything else in mind?
Yes. So in our most recent preprint on the epidemiological models, we go through a series of alternative data types that might be useful and actually realistic to obtain. So at that point, I should mention there is an alternative way to parameterize the sampling models that is commonly used in BEAST and epidemiological literature. So the sampling proportion, the removal rate or become uninfectious rate, and the the effective reproduction ratio. As I mentioned already earlier, the sampling proportion, you might know about that. For example, if you're certain that you're recovering most cases, then you could set the sampling proportion to 1. The extinction rate, mu, might be something you could estimate if you assume that the progression of a disease in an individual doesn't change over time. So basically, COVID cases proceed statistically the same way in March 2020 as they do, let's say, in December 2020. Then you could assume that mu doesn't change over time. And you might even be able to determine it quite accurately by following cases, infections. You see what's the death rate, what's the recovery rate. So what's the death rate of the host and what's the recovery rate of the host, and then you're able to constrain it. Another thing you could constrain is the sampling rate. For that, you essentially need to know the prevalence of the disease in the population. And so we now know that it is realistic to perform general population random seroprevalence surveys. Many countries, states, and cities have done that. So you estimate which fraction of your population has the disease over time, perhaps, at least in principle, it's possible. And you divide by that the rate at which you detect cases using your background sort of detection mechanism, where people come into the clinic because they have symptoms and they get tested, for example. And that's where you get, that way you could estimate psi and put that into your models. We also talk about specific sampling schemes that could help resolve some of these identifiability issues. It gets a little bit more technical, but you can read about these sort of specifically designed sampling schemes in our preprint.
Yeah, I mean, I think that there will continue to be more work, I'm sure, having to do with propagation of errors. If you sort of misestimate some of these parameters, what does that look like?
Yeah, so you can't just fix them and think that it'll solve a problem. If you're going to fix them or constrain them, you better do it in a justified way. If you fix psi at a wrong value, everything else will also be wrong. Roughly, rule of thumb, by the same relative error. So if you get one thing wrong by 50%, you can expect in that order of magnitude of error also for the other parameters then.
Cool. All right, Peter Elf has come back with one more phrasing of his question. He's struggling a little bit with the fact that we have a 200 character limit, which is not my idea. So anyway, the question is how to visualize this unavoidable uncertainty. Given sampling intensity, there's a unique solution, so B should work. So I'm wondering if post hoc incorporating uncertainty analytically using a prior and sampling intensity would be a good idea, or if it would just produce uninterpretably large uncertainties in the parameters. I wonder if he's saying we make lots of different assumptions for what the sampling intensity is, and for each one of those you do a BEAST analysis, say, and then you can basically sort of like use a prior to integrate over those different solutions based on the sampling intensity assumptions using the prior on sampling intensity. So Sounds like an interesting but maybe tough road to travel.
Yeah, I don't know about Matt, but I'm not able to really know how well it's going to work. We do provide code that you can use to explicitly calculate congruent models. So if you have a specific congruent model, let's say skyline model by Beast, you can then take any of these model parameters, pick your own favorite, maybe from a distribution and so on, and then calculate the corresponding congruent models. And maybe that by applying some type of Monte Carlo, going through sort of model space to then see how much variation you would get in the things that interest you, such as the effective reproduction ratio. Maybe that's a possibility, but at this point, I don't know more about this.
Peter says that's not what I meant. So anyway, you two are
sorry.
and so I'll let you hash it out. But thank you very much. Let's see. So Matt, I don't know if maybe you can hear me again now.
Oh yeah, now I can hear you. Sorry, Eric. I had internet issues and cut out, so I was just like drifting in space.
Great. Okay. Well, thank you both.
I'm glad.
Looking forward to the next set of talks, and thanks for a very clear and interesting presentation on some really important work.
Thank you, Eric.
Thank you, Eric, for the invitation.
All right. See ya.
Bye.